Hello everybody and welcome to chapter 5 of advanced functions. We're officially more than halfway there, which is wonderful to think about. So chapter 5 is focusing on trigonometric functions, which is mostly to do with the graphs of the trigonometric ratios that we've learned about, as well as solving trigonometric equations. So essentially it's everything we've done so far just with trigonometric expressions. So let's get started on 5.1, which is concerning about graphs of sine, cosine, and tangent functions. So I split it up into just working with sine and cosine at first, and then working with the tangent graphs. So let's talk about the graphs of sine and cosine. Last year, you've learned how to graph the primary trigonometric ratios in degrees, and now our times have changed and we're working with radians. Essentially, that's the only difference for this part. So now, let's remember some of the basics of the function of sine and cosine. So the graphs of y equals sine of x and y is equals to cos of x are periodic. They also are very similar in shape to the point where one of them is the transformed version of the other, and they both have an amplitude of 1 and a period of 2 pi, or like we learned last year, 360 degrees. Again, this is where your knowledge of radians must be perfect. You need to stop thinking of 90 degrees, for example, or 180 to plot your points. You must be thinking of pi over 2 or pi. Now, as I said, the graphs of sine and cos are very similar to the point where they have the exact same transformations when you apply them. So the transformations could be as the following. First of all, y is equals to sine x plus c. Y is equals to a times sine of x, y is equals to sine of x minus d, and last y is equals to sine of k times x. As you can see, these are the exact same transformations that cosine would have. You might not remember what all of these transformations do, so I will explain them to you right now. So when you add a constant, you're actually vertically translating a graph up or down a couple of units represented by the c value. If c is negative, you're going to translate the graph down. If your c value is positive, then you are going to translate the graph a couple units up. The next one is y is equals to a times sine of x. The a value is referring to your vertical stretch factor. So if a is greater than 1, you're going to be vertically stretching the function. If a is less than 1 but is greater than 0, you're going to be vertically compressing it. Also, if your a value is negative, so less than 0, you're going to be reflecting your graph on the x-axis. Next, we have the transformations of y is equals to sine of x minus d. The d value refers to the horizontal translations of the graph. So in this case, since we have a negative d, it might get a little bit confusing, but essentially if you see -3, for example, that means our d value is positive. And if our d value is positive, you are translating something to the right. If our d value is negative, so you see a plus after the x, that means your d value is negative and you're translating your graph to the left. Lastly, we have the graph of y is equals to sine of k times x. K refers to our horizontal stretch. So here again, it might be a little bit confusing, but when it comes to horizontal stretch, your k value needs to get its, you need to find the reciprocal of the k value to find your factor by which you're either compressing or stretching horizontally. So if k is 3, our factor would be 1 over 3. And if it's 1 over 3, that means we're horizontally compressing it. If k was 1/2, that means we're taking 1 over 1/2, which is 2, which would mean we are horizontally stretching it. Now, this exact same process applies to the cosine functions, which is why I'm not going to go over them. However, I will now show you how to properly graph sine and cos while applying these several of transformations. Okay, so let's get started. First of all, I'm gonna write down the graph that we want to work with, and that would be y is equals to sine of x. So I have already marked out 2 points. This is 1, and this is -1. The reason for that is because we know that the amplitude of the function is 1. The amplitude means the distance from the middle of the function to its maximum point, or the distance between the maximum and minimum divided by 2, which would be the average. So what I want to do now is mark out our other key points, which you should know should be our pi over 2, pi, 3 pi over 2, and then 2 pi. Again, you're probably going to be asked to graph both of, like, for example, -2 pi to 2 pi as your domain, but as long as you know how to do one part, you could do the other. That is what I'm going to show you personally. So what we need to remember for graphing this is actually our key points. Let's first of all try to label what these are. This is pi, this is 3 pi over 2, and this is 2 pi. And then this goes on forever, and then the same thing goes that side. Now, what do we know sine of 0 is? Sine of 0 is 0, so we start off over here, right? I think I'll have to do an x. Then our other key point, I'm gonna actually write it down just so we know. Our other point would be at pi. Again, just remember the unit circle. Using the unit circle, we know that sine of pi is also 0. So we put an x here. Then after full revolution, we're back at 2 pi, which would mean there's a 0 here as well. Now, let's figure out what our value is at 2 pi, or pi over 2, sorry. Pi over 2 would be 90 degrees, if that helps you think. And again, just visualize the unit circle. This is pi over 2, so over here, we're actually at 1. So let's jot down the 1, and then at pi over 3, we're over here. So our value is now -1. Sorry, this is a little bit too big. Now that we found our 5 key points, we can actually draw our function. Okay, I deeply apologize for how wonky this will look, because again, it's really difficult to draw while your hand is on the table and you're looking at a screen. Give me a moment. Okay, that's 1. Make sure when you're actually doing it yourself, it passes through all the points. There you go, that's the best I can do. Also, I've always been taught to add the arrows, because again, it's continuous, it's not stopping at those points, but perhaps your teacher will tell you it's not necessary, then you don't have to do it. So this over here is the graph of y is equals to sine x. Now let's think about the transformations that we learned. So the transformations we had were something like, for example, y is equals to sine of x plus c, y is equals to sine of x minus d, y is equals to a sine of x, and y is equals to sine of kx. So these two are really simple. if I wanted to, for example, move my function down by 1, so we would write y is equals to sine of x minus 1. That would mean that every point that we had before gets moved down by 1. So instead of 0, we have -1. Instead of 1, we have 0. Instead of -1, we now have -2. So we could continue this and then label it, this is -2 now. Again, we could now graph our function. It would look something like this. This is a speed run, in case you're wondering why my lines are super wonky. There you go. That's the graph of y is equals to sine of x minus 1. If you wanted to move it left or right, it's also extremely easy. All we have to account for is moving it left and right. So if we had the function y is equals to sine of x, minus, let's say 2. We know that this 2 is positive, which would mean it is going to the right. So now we're moving all of our original points to the right. This is where it might get a little bit confusing because of the fact that we have 2 units, but we are having our x-axis divided by pi over 2. For that reason, we're actually, if you're given this kind of value, we're gonna have to put this into a calculator and figure out that this is like 1.57. This is 3.14. So 2 would be around like the distance over here. So that's 3 squares. So we're moving everything by 3 squares. But usually what you will actually get is a number like sine of x minus pi over 2. We know that pi over 2 is on our scale, and pi over 2 is 5 squares. So 5 squares is how much we're moving to the right. Be careful with the values that you're given, because there won't be the numbers of squares you have. It will have to follow the legend that you create yourself. Next, a sine of x is also really simple. If we had something like y is equals to 2 sine of x, or for example even like -2 sine of x, we're first gonna, I would flip it in the x-axis. So now we have these points, right? So our graph would look something like that. Something like that. Then we have to multiply it by 2. So now -1 times 2 is -2. 1 times 2 is +2. Sorry, I need to move up now. So this is 2. Same thing goes for these ones. This one is over here now. So let's see. We're moving down by 2. Wrong one. It's this point. Sorry about that. And then over here. Again, you need to make sure that they don't look pointy and actually look well-rounded, because that's how the shapes are actually made. Like, it needs to be curved at the vertexes rather than pointy, because that would be a different function. But as you can see, all we're doing is either applying the negative, and then that would mean flipping it on the x-axis, and then multiplying by the factor we were given, and then graphing that function. So the most complicated one, version for me, is this one. So for example, if we had sine of pi over 2 of x. What does this section mean? Well, first of all, you need to find the factor that we're working with. The factor would be 1 over pi over 2, which is equals to 2 over pi. Now we're going to multiply all the points we have found in our original function by 2 over pi. So 0 times 2 over pi is 0. Pi over 2 times 2 over pi is equals to 1. So our first point will now be at 1. If it's at 1, we again need to learn how to manipulate this graph. I would estimate it's around somewhere here. And since that was the vertex at 1, our new point is over there. Then we have pi times 2 over pi, so now we're at 2, which would be around over here. Then we have 3 pi over 2 times 2 over pi, which would be 3, and the last one would be 4. Again, these points are not that well graphable on our legend over here, because we were using the intervals of pi. However, if you were given something like y is equals to sine of, let's see, negative 4x, that would mean that our factor would be 1 over negative 4 or negative 4, right? If it's negative 4, that means we're reflected on the y-axis. Then, if it's negative 4, that means we're also horizontally compressing it. So we're multiplying pi over 2 times 1 over 4, which would mean pi over 8. Then we're graphing pi over 8, which I would say is like over here. Then, since we're reflected in the y-axis, we need to reflect it. So it would be actually over here as our vertex. Then we're gonna go down, then again back to negative 1, and then back over here. So our graph would look something like this. Again, make sure they're much more curvy and actually reach the points, but it's very difficult to show that with this tool. However, if you want to graph cosine, we have to do the exact same procedure, which I will show you now. We could now proceed to graph y is equals to cos of x. Again, we could think about the unit circle at 0. What are we at? Well, we are at the distance of 1. So we start up top. What we go to our first y-axis, we get a 0. Over here we got a negative 1, and over here we got a 0. So let's graph those points. So 1, 0, negative 1, 0, 1. Now, again, make sure that you have like rounded tops. There you go, that was one of the best rounded tops we've had so far. And then our last one, there you go. That is the graph of y is equals to cos of x. If we wanted to graph it for more than one period, we could go into a negative set, for example. And then again, I said 6 squares, that's pi over 2, but negative. So we'll go down here. Then we're gonna go even more down until we reach negative 1, then go back up. So we're just repeating the shape on the other side. Again, all the transformations that we learned with sine are the exact same for cosine. The only difference is the shape of the graph. Again, to remember how to graph sine and cosine, you need to remember 5 key points. Like, this is literally all you have to remember for this unit. So for sine, you need to remember 0, 0, pi over 2, 1, pi is 0, 3 pi over 2 over 2 is negative 1, and then 2 pi is 0. So every factor of pi will be a 0, and every I would say, like the first factor of pi over 2 would be positive, and the second factor would be negative, and that would keep alternating. For cosine, or let's just write cos, we would have 0, 1, pi over 2, 0, pi of negative 1, 3 pi over 2 as 0, and then 2 pi at 1. That was a really weird way to write it. 2 pi at 1. Also, you might notice that all we have done to transform from this to this is actually move all the values over by 1, right? So when we had pi over 2, we had 1. When we had pi, we had 0. So again, we just took all these values and then moved them down by 1. That would be the same as moving your graph over to the right by pi over 2, which is actually something you need to know for this chapter. Hopefully this little demonstration has refreshed your memory on how to graph sine and cosine, and also just went a little bit more in depth of the 4 transformations that you could do on these graphs. With that being done, let's now discuss the graph of a tangent function. Tan is the last primary trigonometric ratio we need to learn how to graph. Again, the graph of y is equals to tan of x is periodic. However, tan of x is a little bit more special and unique when it comes to its shape and properties. So first of all, the period of the function is actually pi and not 2 pi like for sine and cosine. It also doesn't have an amplitude because the graph has no maximum or minimum values. So it actually approaches positive and negative infinity. The graph is actually undefined for values of x that are odd multiples of pi over 2, which are numbers like 3 pi over 2, negative pi over 2, pi over 2 itself, and stuff like that. Also, the graph becomes asymptotic as the angle approaches these values from the left and right, which is actually why we get the graph approaching to positive and negative infinity. So in case you're wondering why this is the case, why it's not defined at these values, well, it's actually rather simple. All you have to do is recall the identity we learned last class, or the identity you learned a year ago, which is that tan of x is equals to sine of x over cos of x. So if we took that x is equals to pi over 2, we know that cosine would equal to 0. Because again, if we use the unit circle, we know that whenever cosine is at the y-axis, the values would be 0. If cosine of x is equals to 0, that means that our function of sine x over 0 would be undefined because we cannot divide by 0. That is the reason why tan of x is not defined for those values. Again, I will now show you how to graph the function of tan of x. Okay, so let's look at the graph of y is equal to tan of x. Tan of x is a little bit special, but you might recall one of the special triangles, which can easily help. We know that the tan of pi over 4, so tan of pi over 4 is actually equals to 1. That actually lets us have another value that we should be able to graph. For that reason, what I'm going to do is actually use 8 squares. Or actually, yeah, let's go for it. Let's go for 4 squares actually. Pi over 2, pi, then 3 pi over 2, then lastly 2 pi as our domain, or as our x values. As you may recall, the period of this function is actually 1. But I want to graph 2 cycles of it because it'll let you understand the values much more easily. So let's again look back at the unit circle. With this value, we know that tan would be 0 because our cosine is equals to 1 and sine is equals to 0, so 0 divided by 1 is 0. So let's graph that point. Then let's think of what happens as we approach these values over here. So we know that when pi over 4 exists, this will actually give us the value of 1. So let's graph that. Let's say that every 4 squares is 1. So over here we have 1. Then if we went to our negative side, we know using the cast rule that tan should be negative here. So now if we went negative pi over 4 to the left, or we were just at the point of negative pi over 4, we should have a tan value of negative 1. Now using these three values, we could actually draw a graph. You might be surprised by this because it's very little information compared to everything else we had, but that's actually the fun part of tan. The most important thing we have to not forget is actually show our vertical asymptotes. As we learned, tan is not defined for any multiple of pi over 2. So what we know for a fact is that this graph will approach the vertical asymptotes, but they will never reach them. We also know that since it's periodic, every pi, it will repeat. So from 0 to pi, we have a new cycle forming. So at pi, we could once again say that it equals to 0. Then up next, like moving pi over 4 to the right, we would get a positive 1 value. Moving pi over 4 to the left, we get a negative 1 value. And now we could once again graph our branch. This one, I'm trying to make it more long so you could understand the behavior. But again, these should be identical. And you can now start the same thing at 2 pi, at 3 pi, at 4 pi, at negative pi, at negative 7 pi. You will have these identical branches. Another thing we know is that, again, we could apply each of the transformations we've learned before to this function. It'll just look a little bit, it'll be a little bit more difficult for you. For example, if we had y is equals to tan of x minus pi over 2. Well, that means we just moved everything to where it wasn't defined, right? So now our new asymptotes would be at our old zeros. That would be the effect of this transformation. Again, working with these transformations could get a little bit difficult to get used to. However, they all follow the same principles, so the more work you do with them, the more easy they become. Okay, so hopefully that was a good enough explanation for you, but if you feel like you still don't get the hang of it, I would like to show you actually each of these transformations using Desmos. Okay, so I have graphed sine of x. As you could see, we have the intercepts of pi, 2 pi, 3 pi, and then our vertexes are factors of pi over 2, just like we had on our graph. So let's look at what sine of x plus c does. Here we could change the value of c, and as you could see, like for example, let's put it at 3, we have moved everything up by 3. So we had 1, now it's up 4, so 1 plus 3 is equals to 4, that's correct. Negative 1 plus 3 is 2, so that's good. Let's choose like a random point. 3.2 is 2.942, so at 3.2 over here, we should have something of the same value, minus 3, which is correct. So as you can see, that's how that works. Then let's look at x minus t. Over here, again, we're given 1 as our normal value, but if we were to put something like pi over 2, which would make sense, we're graphing it on an actual piece of paper. As you could see, it was moved by pi over 2 across the board. If we made it negative, we would also move it to the left. So again, let's see, pi minus, yep, that's correct. We get a little bit more complicated with a of sine over x. So at 1, it equals to our base graph. But if we made it bigger than 1, as you could see, it gets vertically stretched. If we made it between 1 and 0, it becomes vertically compressed. If we made it negative, it got flipped on the x-axis. And then again, if it's between -1 and 0, it's vertically compressed. And then if it's greater or like smaller than -1, it again becomes vertically stretched. Lastly, we have our most complicated thing, at least personally, which is sine of k over x, which I will show you now. Here it is, it's purple. If it's 1, our base graphs look the same. If we made it greater than 1, as you could see, it is becoming more and more horizontally compressed. If we make it smaller than 1, it's becoming horizontally stretched by that factor, or 1 over this number. If we made it negative, it got flipped on the y-axis. And then again, we followed the same thing. It's honestly really fun. I will add it onto my slide presentations so you could try this out for yourself. Now we could do these exact things, same things, with our other functions. So I will now just quickly put them in. This actually lets you remember what the functions are a lot easier. But again, let's look at cos of x. There it is. What a beauty. Now let's graph cos of x plus c, or c value. Sorry, that's not our c value. This is our c value. Does the exact same properties that it was doing before. Now if we look to d, let's change its color. If we look at d, again, we can translate it by however we want. It's gonna go left and right by whatever unit we have. Next, for our a value, again, it's acting the same idea, and so is our k value. The fun part here is that using these, you could easily prove that sine of x and a transform graph of cosine of x actually exist. So let's see if that is correct. At what point, how much do we actually need to move our functions? Well, if it was negative pi, that doesn't seem right. It was actually too big. But if we had pi over 2, we see that sine of x is equals to cos of x minus pi over 2, which would mean that these graphs are actually the same. Lastly, we could talk about our tan graphs. So let's add the variables into each of these, and then k of x. So this is our basic tan graph. As you can see, 0, 0, pi, 2 pi, as I said. And then our asymptotes, let's graph one of them. X is equals to pi divided by 2 are the following. So you can see they're approaching them, but never actually touching. If we were to add a c value, again, we're going to be moving the graph up and down. So if our c value, there you go, moves it up and down. For our d value, we get to move it left and right. This is pi over 2, like I was saying. Now it's where the old asymptote used to be, but we could of course change it to any other value. If it was for the vertical stretch, which might be a little bit confusing to you, but even though it's approaching negative and positive infinity, we could still change how rapidly it approaches these values, and that is why this graph acts like this. Like if we made this a really, really big number, they look like straight lines at this point, but they will be changing by a very little bit. Lastly, we could talk about our k values, which also just changes how much it is horizontally or compressed or stretched. As you could see, here it is super stretched, and then it got flipped, and now it's becoming horizontally compressed. You could add a lot of these, but it looks really bad if you do that. Overall, again, I hope this just solidified your understanding of how these graphs behave with certain transformations applied to them. With that being said, that was our entire lesson for today. It might have seemed like a review of grade 11, and that's mostly because it was. You should have learned how to do all of these things last year. The only difference now is that, again, you're working with radians, but that shouldn't be a very big problem for you. So I've assigned questions 9, 10, 11, 13, 14, 17, and 19. All of these questions will be either making you create a function or an equation and then graphing it. Again, you're just going to be applying our A, D, C, or K values that we learned today and the appropriate transformations of them. So I'm not going to be going over any of the questions in particular. You should have all the strategies within the 3 examples that I've showed you already of how to graph or how to understand what the transformations do. Overall, I would say this chapter is almost the same as chapter 5.3, which just combines all of the transformations together. So I'm not quite sure why we had to do 5.1 in the first place, but it's a very nice starting point. Again, thank you for listening this far, and I hope you have learned a lot. I can't wait to see you next time. Bye bye!